Hi, this is Abhishek Shetty. Today I'm going to talk about smooth analysis with adaptive adversaries. This is based on joint work with Nika Haghtalab and Tim Roughgarden. There are generally two paradigms in machine learning algorithmic guarantees. In a stochastic or offline setting, the data is generated from a fixed distribution. The learner learns a model using the data and is successful if the error is small under the underlying distribution. Here, we are not concerned about changes in the world. On the other hand, we have the online or the adversarial setting. Here, data is generated by an all-powerful adversary. Success is measured relative to the generated data. If the learner is successful in this setting, then the model is robust to any misspecifications or attacks. Similarly, in algorithm design, we have two general paradigms. In the stochastic setting, the instance is generated from a fixed distribution. Here, we are successful if we find a good solution in expectation. In the worst case setting, the instance is generated by an all-powerful adversary. We are successful if we find a good solution for worst case instances. Many intermediate paradigms have been studied under the banner of beyond worst case analysis. One such model is the smooth analysis model. Smooth analysis was introduced by Spielman and Tang to understand the simplest algorithm. An adversary generates a worst case instance and nature perturbs this slightly with noise. This is intended to capture the noise and lack of precision inherent in the real world. The goal is to perform well with high probability over the perturbation. The modern perspective on this is that the adversary chooses a distribution that does not put too much weight on any single point. In other words, a distribution that is sufficiently anti-concentrated. The goal again is to do well against all such distributions. The model is useful when worst case instances are expected to be brittle and tend to be isolated. Ideally, we get performance comparable to the average case setting. In many real-world scenarios, algorithms need to make immediate and irrevocable decisions in multiple rounds. Examples here are navigating in a self-driving car, deciding vaccine versus control in experiments, game theoretic scenarios where multiple agents are interacting with each other. Here, future instances depend on the actions of the algorithm. For example, in a game, the actions of the other agents depends on the player's actions. This is usually modeled as an adaptive adversary. The goal here is to design algorithms that perform well even against such adaptive adversaries. As before, we would like to use smooth analysis to capture the noise and imprecision inherent even when we have adaptive decision making to get better than worst case guarantees. The main question we would like to study is what the power of adaptive adversaries under the smooth analysis model. Ideal results here would get the same results as the stochastic setting. In particular, we would get around the adaptivity in these interactions. In typical smooth analysis, one uses the anti-concentration given by smoothness to guarantee much better than brittle worst case instances. Unfortunately, in online decision making, the adversary can correlate instances across time and also with the algorithm's actions. This causes a major challenge for preserving and analyzing smoothness using standard techniques. We will use online learning as our first case study for highlighting differences between adaptive and non-adaptive adversaries and developing a general toolbox for smooth analysis with adaptive adversaries. First, we will see offline learning. In offline learning, the learner gets samples from a fixed distribution. The learner makes a prediction and is said to make a mistake if the prediction disagrees with the true label. The regret is measured as the difference between the number of mistakes the algorithm makes and the number of mistakes the best hypothesis in hindsight makes. The aim is to make the average regret go to 0. In the online learning setting, the points are picked adversarially, potentially depending on the actions of the learner. Again, the learner is said to make a mistake if its prediction disagrees with the label. The regret is defined similarly as the difference between the mistakes of the algorithm and the best hypothesis in hindsight. We want to make the average regret go to 0 as t tends to infinity. Let us look at a worst case instance for online learning. Consider the class of thresholds in one dimension. Note that the algorithm has to predict labels for adaptively and adversarially chosen points. Let us see how that goes. The adversary first gives us a half. The algorithm has to decide whether this is a +1 or a -1. The algorithm says -1, but the adversary says, oh, it's actually +1. The next point is a quarter. The algorithm says +1, but the adversary says -1. The next point is 3/8. The algorithm says +1, but the adversary says -1. Note that there is a consistent hypothesis with all the adversaries labels. In general, the point is that no matter what the algorithm does, there is still a path that has the same property of forcing the algorithm to make many mistakes while keeping a perfect hypothesis still feasible. Thus, the algorithm is forced to make a mistake every round and thus makes t mistakes. As we saw, even for simple classes, online learning can be much more difficult than the offline learning. This is formally seen by noting that the regret for a class in online learning depends on the Littlestone dimension, while for offline learning, it depends only on the VC dimension. This is interpreted as an impossibility result since the Littlestone dimension can be much larger than the VC dimension. Even for simple classes like thresholds, the Littlestone dimension is infinite while the VC dimension is constant. This leads us to the question of whether we can get meaningful guarantees in a beyond worst case setup. We look at a smooth analysis setup of online learning. Here, a learner picks a function while the adversary picks an instance x bar t and y bar t. This is randomly perturbed to an instance xt, yt. Regret is measured as before as the difference between the mistakes of the learner and the best action in hindsight. Equivalently, this can be seen as the following process. The adversary picks a distribution adaptively such that the density is bounded by a 1/sigma factor from the uniform distribution. We will refer to such distributions as sigma smooth distributions. The instance is drawn from these distributions. Note that adaptivity here means that the choice of di at time I could depend on all the previous draws. We want low regret in expectation over d1 to dt. Now let us look at the landscape in this setup. Recall from before that the regret in the online setting depended on the Littlestone dimension. We show that in the smooth model, even with adaptive adversary, the regret is bounded by only a function of the VC dimension. In particular, we show that the regret is bounded by square root of t times the VC dimension times log of 1/sigma. Thus, we show that the class is learnable in the smooth online model if and only if it is learnable under the uniform distribution. As a warm-up, let us look at non-adaptive adversaries. Here, the adversaries pick d1 to dt a priori, and the instances are sampled from these distributions. The main observation here is that the samples across time are statistically independent. Because of the independence, we can apply techniques from statistical learning theory. The main idea here is that we can approximate the potentially large class H with a small class H prime that well approximates it. Given such an approximation, we run a standard online learning algorithm using H prime. The regret would decompose as the regret of the class H prime plus the approximation error. The approximation notion we look at is that of a net under the uniform distribution. This, along with smoothness, guarantees that there is always a H proxy for each H such that the density in the symmetric difference is small. For each difference set, we have some anti-concentration which guarantees that there is not too many points that fall into it. Even though there are a large number of different sets, we can use VC theory since the instances are independent. What goes wrong in the online case? Here, the instances are not independent since they are generated by an adaptive adversary. The adversary could potentially concentrate on a small difference set through correlations. Formally, here is the technical challenge. Consider a class G of possibly infinite size such that the expectation under the uniform distribution is at most epsilon. Let d1 to dt be an adaptive sequence of smooth distributions. We want to upper bound the expected max from the class G of the sum of G evaluated on samples from these distributions. Though each G has small expectation, the difficulty is in dealing with the maximum. The challenge is that samples x1 to xt are not independent. The broad question is how to preserve anti-concentration when a sequence of smooth distributions is adaptively chosen. Even though each sigma smooth distribution is anti-concentrated, the main issue is dealing with the arbitrary correlations between the distributions. Towards a solution, let's quickly recall the notion of couplings. A coupling between two distributions x and z is a joint distribution such that the first margin is distributed according to x and the second margin is distributed according to z. Usually, we want to have a nice property between the draws x and z. This notion is useful when we want to compare expectations of random variables. And this is extensively used in probability theory, for example in the theory of Markov chains and in optimal transfer. The main technique we'll use to prove our result is to couple smooth adaptive adversaries with samples from the uniform distribution. What property do we want from our coupling? A property that would be useful is that if we draw x1 to xt from the smooth adaptive sequence of distributions, there is a sequence of uniform random variables z1 to zkt such that x1 to xt is a subset of z1 to zkt. Note that the number of samples from the uniform distribution is larger than the number of samples from the smooth distribution. Why would this be useful? We can bound the loss on the samples x1 to xt in terms of the loss on z1 to zkt. Note that the loss on z1 to zkt is exactly the average case setting. Let us formally look at our coupling result. For any sequence of t adaptively chosen distributions, there is a coupling such that x1 to xkt are drawn from the smooth distributions, z1 to zkt are independent and drawn from the uniform distribution. Here, k is approximately 1 over sigma. With high probability, we have that the set x1 to xkt is a subset of the set z1 to zkt. Why is this useful? The uniform distribution is not concentrated, thus we have that x1 to xkt is not either. We want to say the difference set between h and h proxy does not contain too many points x1 to xt. It thus suffices to say it does not contain too many points z1 to zkt. z1 to zkt are IID and uniform, hence are guaranteed to be scattered. Thus, adaptive smooth adversaries can be much worse than stochastic adversaries on a slightly longer time scale. Recall that we wanted to show that the regret is bounded by square root of t times the VC dimension. First, we take a finite approximation of h, let's call it h prime. Given h prime, we'll use a standard online learning algorithm with h prime and pay an additional regret given by the approximation error. How do we pick h prime? We pick h prime such that under the uniform distribution, the difference between h and h proxy is at most epsilon. This also works nicely for smooth distributions. The expected number of points in the difference set is at most t times epsilon over sigma. We then apply the coupling. The approximation error is given by the number of points from the smooth adaptive distributions falling in the difference set. This is at most the number of points from kt samples from the uniform distribution falling in the difference set. This follows from the nice property of the coupling which says that x1 to xt is a subset of z1 to zkt. Formally, denote by x the set x1 to xt and by z the set z1 to zkt. We have x is a subset of z with high probability. Let G be the class of all differences between h and h proxy. Since counting the number of points in a set is a monotone set function, we have that for every G, the sum from x is at most the sum taking elements from z. Then, the expected max under x is bounded by the expected max under z. By construction, G is based on a net, and thus we have the expectation under the uniform distribution of G is at most epsilon. But we can bound the expected max under the uniform distribution using the VC theorem since the samples are independent. Thus, we get the regret to be bounded by square root of log of size of h prime times t plus epsilon times kt plus square root of epsilon times kt times d, the VC dimension. Note that we can always take the size of h prime to be 1 over epsilon to the d. Thus, we get our result by choosing epsilon to be sigma over t and noting that k is approximately 1 over sigma. The main message is that when we want to be robust over t rounds of interactions with an adaptive smooth adversary, we can use the coupling to lift classical analysis from the stochastic setting to use in this setting. The main recipe for applying this is, first solve the problem in the uniform case. Isolate the steps that depend on anti-concentration. This is usually in the form of some potential function or some other monotone set function that measures the concentration. Apply the coupling lemma. Replace t rounds of an adaptive adversaries to approximately t over sigma uniformly generated random variables. Update the dependence for t over sigma random variables in the first step. The subset property tells us that the potential or the monotone set function can only increase. But since z1 to z t over sigma are uniform, this can only moderately increase the concentration. Put this all back together in the original algorithm and the analysis technique. This recipe has several applications. We saw online learning earlier in the talk. We will see online discrepancy minimization briefly next. Other applications include data-driven algorithm design. We also proved beyond worst-case guarantees for differential privacy in earlier work using slightly different techniques. We apply this recipe in the setting of online discrepancy minimization. Here, a sequence of vectors v1 to vt arrives from the L2 ball online. We need to assign signs ai to be plus or minus 1. The goal is to maintain the infinity norm of the sign sum of the vectors to be small. For worst case adaptive adversaries, we can get a lower bound of square root t. In the stochastic setting or the setting of oblivious adversaries, previous work have shown a bound of polylog nt. We show that for smooth adaptive adversaries with isotropic distributions, we can get a polylog nt over sigma bound on the discrepancy. Note that the discrepancy itself is not a monotone set function in the vectors, but BJSS20 use a potential function argument to keep track of the discrepancy. Our proof follows by applying the recipe and by exploiting the potential function arguments. Our results apply smooth analysis beyond runtime analysis to understand fundamental information theoretic limits of learnability. Understanding further applications of these techniques is an interesting future direction. Some open problems here are: reductions from adaptive smooth to stochastic setting usually respects efficient algorithms, but this is not the case in the setting of online learning where we only get exponential time algorithms. One question is whether there's a computational statistical gap in the smooth analysis setting of online learning. Thank you for paying attention.